Guten Morgen zusammen. Heute ist der 23. April 2026, Business Intelligence Vorlesung. We will see today a method called Principal Component Analysis, in short PCA. Okay, it's a method that helps us reduce the dimensionality of data sets, and in business is very useful to reduce large data sets to the most important ones and get most information out of them. So imagine this graphical intuition I painted here, X and Y, just 2 dimensions to make it easy, are 2 KPIs, maybe cost and throughput or lead time or something like that. Okay, so 2 KPIs. And the question here is, what is the direction that helps us get the most of this data set? In which direction should we look at the data to get the most information? If we would only have one direction, I guess it's very intuitive that the best direction would be something like this. Okay, some vector like that. That direction helps us understand the data. So imagine now you are looking at the data here. You're looking from here, okay, to the data. What you would see is a very pointy Gauss curve. Okay, so you know this from statistics. This has a very small standard deviation. Okay, all the data that you see here are in a very small distance, in a very small range from this direction, if we look at the data in this direction. Okay, so the direction that gives us the minimum, the direction that shows the minimal sigma standard deviation is called principal component number 1 or PC1. Okay. This is a graphical intuition. We will see in a couple minutes how we can do this mathematically, but for now this is enough. So the second, we have 2 dimensions, so we need 2 principal components. The second principal component is perpendicular, senkrecht. Okay, so if this one could be called PC1 or something like B1, vector 1. Okay, the second one is called PC2 or V2. And the Gauss curve, if we look again, if we sit down here and we look in this direction to the data, then we see a very different picture. We see a very wide standard deviation, so very big standard deviation. Okay, so perpendicular to PC1, we have PC2 and sigma 2 is much bigger than sigma 1. Okay, standard deviation, you know, shows the variability in the system. Okay. So, any questions to this, let's say, intuition? Or irgendwelche Fragen zu der Intuition? In German gerne. No. So, there is I can give you a definition of what a principal component is. So the principal components are the eigenvectors of the covariance, or of the covariance, yes, matrix. Okay. So this is the statistical definition that we use for the principal components. So from statistics, you know that the covariance matrix of a system with n variables in our case n KPIs, okay, in the management system. So the covariance matrix of the system with n variables x1, x2, xn equals something like this: variance of x1, covariance of x1, x2, covariance of x1, xn, then covariance of x1, x2, variance of x2, covariance of x2, xn, covariance of x1, xn, covariance of x2, xn, and variance of xn. So this is the definition of the covariance matrix. It's a symmetric matrix. Okay. So if we have E and J, I and J from 1 to n, we can say that the variance of x sub E equals the sum of x sub E minus x sub E mean divided by n minus 1. And the covariance, let's do it in English, covariance of x sub I, x sub j is the sum of x sub I minus x sub I mean value times y sub, x sub j j mean value divided by n minus 1. Okay. So, and with this information, this is already known from the lecture statistics. Okay, so nothing new under the sun so far. Any questions? Könnt ihr kurz Feedback geben, Daumen hoch oder so, dass es verständlich war. So, okay, vielen Dank. Hier steht die Hauptkomponenten, the principal components are the eigenvectors of this matrix. Okay, so this is something maybe new and something that we need to take care of. So first thing, let's make an example to calculate the covariance matrix. So a company has a management system with two KPIs. KPIs meaning key performance indicator, lead time, in German Durchlaufzeit, and cost per unit, in German Kosten pro Stück. Please calculate the covariance matrix. Okay, so lead time is measured in days, has following values: 17, 19, 21, 27. And this is we're going to call this the variable x. And cost, it has the units euros per part or per unit. It has the values 7, 11, 12, and 15. And this has the name y or epsilon. Okay, so the mean value of x is 17 plus 19 plus 21 plus 27 divided by 4. This yields 21. The mean value of y is 7 plus 11 plus 12 plus 15 divided by 4. This is going to yield 11.25. Okay. So to calculate the covariance matrix, we need the variance of x. For that, we need the sum of x sub e minus x sub e Mittelwert square, or x something like that, better, divided by n minus 1. Okay, so this is 17 minus 21 square plus 19 minus 21 square plus 21 minus 21 square plus 27 minus 21 square divided by 4 minus 1. And if I have not made mistakes, this delivers 18.7. Any questions on this? I mean, this is already known from statistic. Variance of epsilon, same game. Okay, so 7 minus 11.25 square plus 11 minus 11.25 square plus 12 minus 11.25 square plus 15 minus 11.25 square divided by 4 minus 1. And this is going to deliver 10.9. And the covariance of x and y is x sub e minus x Mittelwert, epsilon sub e minus epsilon Mittelwert, n minus 1. So if we do this again, 17 minus 21 times 7 minus 11.25 plus 19 minus 21 times 11 minus 11.25 plus 21 minus 21 times 12 minus 11.25 plus 27 minus 21 times 15 minus 11.25, all divided by 4 minus 1, and this yields 13.3. So a little note for those of you that are going to write the exam. In the exam is parametrisiert, parameterized, so you have a matrical number, let's say 2, 3, 7, 6, 3, 9. Okay, so this is the first digit is A, B, C, D, E, F. Okay, so each number has a letter attached to it, and when I give you the numbers of the lead time, I will not say 7, I will say 7 plus 2 times A, and then 13 plus 3 times B, and so on. Okay? So whenever you see the A, you must put 2. So 7 plus 2 times A is 4. 13 plus 3 times B is 9, and so on. So this is 11, and then 22. Okay? In this manner, the exam has the same questions for everybody, but different numbers. This makes it more difficult to cheat. Okay? This is important if you are going to write the exam. Make sure you internalize this. I say this and it's on a video because this is something that it stays. Because some of you or some of your predecessors have tried to invalidate some exam questions because they pretended I did not explain it. It's just not the case, okay? All right, so any questions on this? So the covariance matrix is something like 18.7, 13.3, 13.3, and then 10.9. Okay, so this is the covariance matrix of our management system. Now, we want to calculate the eigenvectors and eigenvalues of this covariance matrix. And in order to do so, we need to do some calculations. So the eigenvectors and eigenvalues both called phi and lambda can be calculated as follows. If we call the covariance matrix, let's say A, okay, then eigenvectors and eigenvalues verify this equation. Okay, so this means that the determinant of A minus lambda E is the identity matrix, equals 0. From there we get lambda, and from each lambda we get each eigenvector. Okay, so this is our plan to solve the problem. So let's see how this is done in reality. So the determinant of A, we can write A again, 18.7, 13.3, 13.3, 10.9, minus lambda identity matrix 1, 0, 0, 1 should equal 0. So what we get is that the determinant of 18.7 minus lambda 13.3, 13.3, and then 10.9 minus lambda equals 0. This yields 18.7 minus lambda times 10.9 minus lambda minus 13.3 square equals 0. Just a note for you, for those of you that don't remember how to calculate a determinant. If this is the determinant, then this is A times D minus C times B. Okay, so this is going to yield lambda square minus 29.6 lambda plus 26.2 equals 0. This is then going to yield lambda equal 29.6 plus minus 29.6 square minus 4 times 26.2 divided by 2. This is because when we have an equation, again, this is very basic, then the roots of this polynomial are minus b plus minus b squared minus 4 times ac divided by 2a. Okay, so if we solve this, we get two values of lambda 1 with the plus 28.7, lambda 2 with the minus 0.9. Okay, any questions on this? Könnt ihr mir Daumen hoch oder Daumen runter geben? Falls irgendwas ist, bitte einfach Mikrofon aufmachen und einfach schießen. Okay, das ist überhaupt kein Thema, das lassen wir hier. Gut, das sind die Eigenwerte. Die brauchen wir nachher. Also nicht vergessen, aber jetzt now we're looking for the eigenvectors on the first thing. So 28.7. We take the first eigenvector, which is the biggest. And so notice that the first eigenvector is 28.7 and the second eigenvalue, sorry, 28.7, and the second eigenvalue is only 0.9, so way smaller, and this will have a meaning later on for your management system. So because we want to solve this, we want to go ahead and say A times V1 equals lambda 1 V1. So to solve this equation is a piece of cake. Let's do it slowly. If you don't understand any step, just say it, okay? So I write here the first vector, V11, V12 equals 28.7, V11, V12. And this is going to be like 18.7 V11 plus 13.3 V12 equals 28.7 V11. Okay, I'm just multiplying this time this and this time this equals this time this. Okay, so these are two equations in one. This yields that V11 equals 1.33 V12. Okay. So if V11 equals 1, then that's why I always fix the first component to 1. Then V12 equals 0.75. Then our first eigenvector is 1, 0.75. Okay? And this is important. Any questions on how I did solve this? No questions? Okay, so the second eigenvalue (0.9), so A times V2 equals lambda 2 times V2. This yields following equation. Okay, so this is going to be delivering 18.7 times V21 plus 13.3 times V22 equals 0.9 V21. Okay, so this delivers that 17.5 V21 equals minus 13.3 V22. So fixing the first one to 1, we get that the second eigenvector is minus no, sorry, fixing the second one. It doesn't matter, but so this is correct. Okay. So this is the second eigenvector, and now let's see what this whole thing means geometrically. Okay. But first of all, any questions how I did solve this? One question always comes is, I fix this, so I put here a 1, and then the other just results, okay, automatically. If I fix the other one, it's just a different length of the vector, but it's the same direction. So what this means geometrically is following, okay? So I have, remember above we have two KPIs, one the lead time with numbers 17, 19, 21, and 27, and the cost with numbers 7, 11, 12, and 15. Let's paint this in a rough scala to understand what we are doing. So if this is x and this is epsilon, okay? So the first point is, let's say this is 5, 10, 15, 20, 25, 30, okay? And this again 5, 10, 15, and so on. So the first point is 17 and 7, so something here somewhere. Second point is 19 and 11, somewhere here. 21 and 12, and 15, 27 and 15, so here, okay? And our solution was that the first eigenvector is 1, 0.75. So if we zoom in here and we say, okay, this is 1 and this is 1, okay, so 1, 1. Our first vector goes parallel to the direction 1 and 0.75. Okay, so something like this. This is our first vector. One, 0.75. And guess what? This is the direction that best explains our data. Okay? So these two vectors are exactly the same in direction. Okay? They're parallel. Is this understandable? The other vector is minus 0.75. So in minus 0.75 and plus 1. So basically perpendicular to the other, it will be something like this. This is the second vector, minus 0.751. Okay, perpendicular. So if we take this, we can make it just perpendicular, and this is the second eigenvector of our management system. Both are, as I said, very important, perpendicular to each other. Okay, so this is the first takeaway. The second and most important takeaway is with this information of the eigenvalues, these eigenvalues, we can say how much of the system we are explaining with each direction. Okay? So remember our eigenvalues were lambda 1, 28.7, and lambda 2, 0.9. And now we ask the question, how much variability can be explained with each eigenvector? Okay? So remember, the variability explained with the first eigenvector is lambda 1 divided by lambda 1 plus lambda 2. So this is 28.7 divided by 28.7 plus 0.9. So it's around 97% of the variability. This means that I can explain 97% of the variability in the management system with only one direction. I don't need two, I only need one direction to explain 97% of the variability of the system. The second eigenvalue is 0.9 divided by 28.7 plus 0.9. That is around 3%. So as future leaders, each KPI that you measure costs you money. Okay? Because it costs you money, you want to optimize the KPIs you're measuring. So make sure that you perform some PCA to your management system to find out which ones are the most important KPIs to help you only measure the KPIs that are relevant, that explain your system. Because chances are that some of the KPIs you're measuring are not useful for your system. Okay? Very important. Any questions? So, no questions? Alles in Ordnung? Irgendwelche Fragen? Anregungen? Sollte ich Ihnen was wiederholen? Nein? Okay. So, another example. A company has a 3-dimensional management system with lead time, cost, and quality. Please give the PCA and give a management interpretation. Okay, so the numbers are lead time, variable x, going to be 7, 11, 9, 13, and 8. Measure in days. Then cost, variable y, 317, 350, 327, 365, 330. Measure in euros per unit. And quality, Z, 3,718, 3,970, 3,780, 3,790, and 3,810. Measured in parts per million. Parts per million is the number of wrong parts per million produced. So what is the first thing that you see here with your eyes of leaders in this system? So the first thing that you must see here is that we are moving the lead on the lead time. We are moving on the units. Here we are moving on the hundreds. Here we are moving on the thousand. So we cannot compare. We cannot, the covariance doesn't make any sense because the distance of 2 units in the lead time has not the same meaning of the distance in 2 units of in the quality. Okay? So what we need to do is we need to normalize. Perform normalization to make the data set homogeneous. If you don't normalize in the exam, you have not understood what is behind the concept, and you don't get points. Okay, so make sure to do it. So we bring the data between 0 and 1. How do we do it? We take, so in order to bring one data between 0 and 1, we take this data point, subtract the minimum of the time series, divided by the maximum minus the minimum. Okay, so this is what we do. We have the lead time star, meaning 7 minus the minimum in the time series is 7, divided by the maximum is 13 minus 7. Okay, then 11 minus the minimum, 7 divided by 13 minus the minimum, 7. Then 9 minus the minimum divided by 13 minus 7. Then 13 minus the minimum divided by 13 minus 7, and then 8 minus the minimum divided by 13 minus 7. So this is 0, 0.67, 0.33, 1, and 0.17. So any question on how I did this? Is that okay? No questions? Good. Then I go ahead and perform the cost. Basically the same, 317 minus 317 divided by 365 minus 317, then 350 minus 317 divided by 365 minus 317, 327 minus 317 divided by 365 minus 317, 365 minus 317 divided by 365 minus 317, and then 330 minus 317 divided by 365 minus 317. This yields 0, 0.69, 0.21, 1, and 0.27. And then the quality, Q star, I just do it faster, okay? It's just same logic, you get my point. Of course, in the exam, you need to put all the things together. Remember that in the exam, all the numbers will be different for everybody because of this concept of the matricial numa, okay? So there is no point in looking around, and because you need to show all the calculations, then this is, yeah. So now we want to have the covariance matrix. With this data, let's say A star. Okay, so now let's start. We need the X mean value of the data above. If you perform the mean value of this, okay, I'm not gonna do it again. I'll just give you the result 434. I highlight again, in the exam you have to show me all the equations, okay? Just for the sake of speed in the lecture. Then the variance if you do the calculations, it's going to be 0.16. The variance of y is going to be 0.14, and the variance of z is going to be 0.14 also. Then the covariance x epsilon is going to be 0.14. The covariance of x and z is going to be 0.067, and the covariance of y and z is going to be 0.067. So if we plug in this data, here we get 0.16, 0.14, 0.14, 0.16. Wait, no, this is wrong. This is 16. Then 0.067, 0.067, 0.067, 0.067, and then 0.14. Okay. So to calculate the mean, the eigenvectors and eigenvalues of this exactly is a little bit too tricky. So that's why we approximate A with a star and make 0.067 to 0. So the approximation of 0 star is A with a hat, and this is this equation, which is not an exact result, but it is very close and it's much easier to calculate. So what are the eigenvalues of this equation and the eigenvectors, I guess. So we need to solve this. So the determinant of 0.16 minus lambda, 0.14, 0, 0.14, 0.16 minus lambda, 0, 0, 0, 0.14 minus lambda equals 0. This yields 0.14 minus lambda times 0.16 minus lambda square minus 0.14 square equals 0. To make this step, I made this. The determinant of A, B, C, D, E, F, G, H, I equals A times E times I plus B times D plus H plus, times I plus A times H times F minus C times E times G minus B this is wrong, DHC B times D times I. This is also wrong. B times F times G. And then E times H times F. Okay, so this is the equation. Let me check again. DHC, BFG, and then CEG, BDI, and AHF. Yes. Okay, so this is the determinant of a 3x3 matrix. You need to know this. So to solve this, one of the eigenvalues is direct, okay, from here. This is the second eigenvalue, and then the other two eigenvalues we get by solving lambda square minus 0.32 lambda plus 0.006 equals 0. So lambda equals 0.32 plus minus square root of 0.078 divided by 2. So this yields lambda 1 equals 0.3 and lambda 3, sorry, 0.02. Okay, so these are our three eigenvalues of the system, of the approximated system. Okay, so any questions so far? Okay, then we go ahead and say lambda 1 equals 0.3. Then A times V1 equals lambda 1 V1. So we do it 0.16, 0.14, 0, 0.14, 0.16, 0, 0, 0, 0.14. First eigenvector equals first eigenvalue 0.3 times first eigenvector. And now we just need to multiply. So from the last one goes 0.14 times 1v3, v13 equal 0.3 times v13. This means that v13 has to be 0. Is the only solution. And the second goes like this, 0.14 v12 equals 0.3 v11. This yields that v11 equals v12. So if v11 equals 1, we have our first eigenvector going ahead like this, 1, 1, 0. Okay, the variability explained by this eigenvector is 0.3 divided by 0.3 plus 0.14 plus 0.02 equal 65%. The management interpretation is that taking only into consideration lead time and cost, no quality because it's 0, we can explain 65% of the variability of the system. So we could likely go ahead and just describe the system with 2 KPIs and still be very successful. Okay? So this is for the first eigenvector, eigenvalue. If we take the second, we have our matrix. Solve it in the same manner, 0.16, 0.14, 0, 0.14, 0.16, 0, 0, 0, 0.14, V21, V22, V23 equal 0.14, V21, V22, V23. Okay, so what we get is that 0.14 V23 equals 0.14 V23. So V23 can be any value, so let's take V23 equal 1. The reason why this is because we made an approximation, okay? In reality, the real system wouldn't go like this, but this is an approximation, so we take that. And then the second is that 0.16 V21 plus 0.14 V22 equals 0.14 V21. This yields that 0.14 V22 equals minus 0.02 V21. So if V21 is 1, then V22 is minus 7. As a result, the second eigenvector is 1, minus 7, and 1. So the variability explained by the second eigenvector is 0.14 divided by 0.3 plus 0.14 plus 0.02 equal 30%. Okay. Here the management interpretation is that with the second eigenvector, we can explain up to 95% of the variability of the system, okay? And this is already a lot, so we can easily discard the third for not being so relevant. But let's do it for the sake of completeness. A with a hot V3 equals 0.02 V3, meaning let me paint lambda 3. So this is 0.16, 0.14, 0, 0.14, 0.16, 0, 0, 0, 0.14, V31, V32, V33 equals 0.02 V, oh sorry, oh man, V31, V32, V33. Okay. And doing this, we get again that V33 times 0.14 equal 0.02 V33, meaning that V33 must be 0, okay? So what we get is the 0.16 V31 plus 0.14 V32 equals 0.02 V31. If we solve this, we get that V31 equals 0.14 V32 divided by minus 0.14, so equals minus V32. As a result, if we fix the first one to 1, then we get 1, minus 1, and 0. The variability explained. By V3 equals 0.02 divided by 0.3 plus 0.14 plus 0.02, equaling only 5%. So the management interpretation is that the third eigenvector explains only 5% of the whole variability of the system, which is very little. Okay? Any questions? Okay, well then we make a little break until 11:05 and then we continue. So hello again, we are going to continue the lecture with a new method called nemawashi. This is Japanese, means to prepare the ground. This method visualizes the dynamics of the organization through its KPIs, okay? So it's a visualization method. And the best thing is to explain it with an example. So in the example, a company or a KPI system is three-dimensional and has following data. Please implement nemawashi to visualize the organizational dynamics. Okay, so the data are as follow. Let's say we have here quality measured in ppm. Then we have delivery rate measured in percentage. We have cost measures in euros per unit. And we have different calendar weeks, 300, 91, and 17. Calendar week 2, 700, 93, and 18. Calendar week 3, 1800, 89, and 16. Calendar week 4, I'm having problems with my program, so wait a moment. Start it again. Now seems to work better. Calendar week 4, 1500, 92, and 15, and calendar week 5, 1300, 95, and 16. So the first thing you notice again, the scale of the system of the three KPIs is different. Okay, so we need to normalize. In order to do so, we normalize each KPI between 0 and 1. So each one of the columns is normalized between 0 and 1 before we can even start comparing them. So Q star, delivery rate star, and then cost star. I do the first one, 300 minus the minimum divided by 300 minus the minimum equals 1. 91 minus 89 divided by 95 minus 89, 0.33. And 17 minus 15 divided by 18 minus 15 equals 0.66. Okay, and for the rest is exactly the same. I just put the results. In the exam, you need to make sure you write every single calculation, okay? It's important so that you get all the points. If you don't write the calculations, then I don't know if you made it or you looked to your neighbors. 0.5, 0, calendar week 5, and 0, 1, and 0.33. So as you notice, here is simple. Each column has one value of 1 and one value of 0, which correspond to the minimum and the maximum value, okay? So this is a normalization. Then the second step is to normalize the temporal axis. This normalization is a little bit different so that all the values add up to 1, okay? So in order to perform so, we have again Q star star, second normalization, delivery rate, star star, cost, star star. And in the calendar week 1, in order for the three values in the temporal, 1, 0.33, and 0.66 to add up to 1, what we do is we take 1 divided by the sum (0.5), then 0.33 divided by the sum, (0.165), and then 0.66 divided by the sum equals 0.33. So now you see these three values add up to 1. Okay, we saw this already in previous lectures when we did the backpropagation last layer. So for the others is exactly the same. (0.297) 0.66 divided by 0.7 plus 0.66 plus 1 equals 0.28, and then 1 divided by 0.7 plus 0.66 plus 1 equaling 0.42. So for calendar week 3, we have exactly the same, 0.43, 0, and 0.57. Then calendar week 4, 0.167, 0.833, and then 0, and calendar week 5, 0, 0.75, and 0.25. Okay, so this is the data we have. Now we want to represent this data graphically. Okay, How do we do it? Well, we do following. Let me copy the data again in small. Quality, start, delivery rate. So 0.5, 0.165, 0.33, 0.297, 0.28, 0.42, 0.43, 0.57. I'm just copying it, okay? So 0.167, 0.833, 0, and then 0, 0.75, 0.25. Good. This is just the same data as above. So how do we represent this graphically? Now pay attention, please. We use a so-called simplex, and you have the video later on to look step by step how this whole thing is happening. So at each one, this is a representation of 3 KPIs in 2 dimensions, okay? So what we are going to have is this vertex represents the quality KPI equal to 1. And then if we put a line between this point and the midpoint of the other triangle, like this, okay? So this line all the points of this line have values of quality equal to 0. And all the points of this line have values of quality equal to 1. In the middle, somewhere here, have values of quality equal to 0.5, and so on, okay? So this point is a value Q star star equal to 0. If we take this vertex, we have cost, maybe cost star star equal to 1. And then duplicate here. Like this. This point has cost star star equal to 0, and all the points in this line also, okay? And then the vertical, okay, these 3 should be in the same, should be in the same point. So this point is cost 0, and the vertical, this is delivery rate star star equal to 1, and this point and all the points in this horizontal have delivery rate star star equal to 0. Okay, so this is our simplex representation. So now let's represent all the points of the calendar weeks. Okay, for each point we only need 2 because they add up all to 1. So if we have 2, the third one is already determined. So now please pay attention. I'm going to make the points in certain colors. So this point in the middle has coordinates 0.5, 0.5, 0.5. Okay. So we know that all the points going through this point, through this line, have quality start equal to 0, and all the points going through this line have quality start equal to 0.5. So the calendar week point must be on this blue line. Okay. Then we take the value of delivery rate 0.165. Okay, if this point is the 0.5 and this point is the 0, the 0.165 is somewhere here. Okay, so this is the delivery rate start equal 0.165. And where both points intersect, here is our point from calendar week 1. Okay? This makes sense? So now let's represent the second point. I'll take another color. So I'm taking another color. So the second point is going to be quality 0.3. So if this is 0.5 and this is 0, it's somewhere here. Okay. So this line is the line representing quality star 0.297, and this line is going to be representing the delivery rate 0.33 or 0.28. Sorry. So this is delivery rate start equals 0.28. So the calendar week 2 is here. So de facto, our system is moving from calendar week 1 to calendar week 2 in this manner. Okay, so this way. And this is the dynamics of the organization. Okay. So for calendar week 3, it's a little bit easier because we know that all these points have a delivery rate 0. Okay, so we know that the line is on this horizontal, and the quality is 0.43. Okay, so we can take that as information. I change the color. This is the quality for 0. This is the quality 0.5, so 0.43 is somewhere here. Okay, so these are all the points of quality. Sorry, let's take the right color. This is the points of quality start equals 0.43. And because we know that the delivery rate is 0, this is our point for calendar week 3. So we know that our system is moving again. And this is the dynamics to calendar week 3. Okay? Then for the fourth one, we take the cost is 0, so it's on this line because this is 0. And we take for instance, the quality 0.165. So always with parallels, so it's not very difficult. Let's take another color. Let's say this. So this line is for quality. Sorry, I took gray. So quality star 0.167, sorry. And then we know that our calendar week 4 is right there. So the company is moving again. System is moving like this. Okay. And the last is calendar week 5 is quality 0, so it's going to be here 0. It's going to be on this line, and then delivery rate 0.75. Let's take another different color. So delivery rate 0.75 is, if this is 0.5, somewhere here. So this is delivery rate 0.75. And we know that this calendar week 5 will be right there. So the company is moving again to this point. Okay, so the overall dynamics of the company have been represented like this. Okay. Any questions? So we can interpret the dynamics Okay, so the system is in alignment. This word is important, okay? On a time point t sub j, if the distance between t sub j minus 2 and t sub j minus 1 is bigger than the distance between t sub j minus 1 and t sub j. In other words, the distance between calendar week 1 and calendar week 2, this distance is smaller than the distance between calendar week 2 and calendar week 3. So distance increase, so we have no alignment in calendar week 3. The distance between calendar week 2, calendar week 3 this distance, is again smaller than the distance between calendar week 3 and calendar week 4. So because this distance is very big, okay? So again, distance increase, so no alignment. In calendar week 4, and the distance between calendar week 3 and 4 is bigger than the distance between calendar 4 and calendar 5. So there is alignment in calendar week 5. Okay. In a sense, okay, if you want to make an intuition, if the trajectory behaves like this, okay, so always closer to a certain equilibrium, which is desired, we have equilibrium, we have control under the organization under control, and then we can say we have alignment. So within the circle, the organization is under control and then in alignment. Okay? This is the intuition to it. All right, so today we learned Nemawashi and we learned principal component analysis. Please make sure you go through this and give yourselves more examples to get some speed in the event that I asked this in the exam. Okay? Any questions?